Hi everybody! In today's video I'd like to show you how to make a simple electric magnet. You may recall this experiment from your physics class or crafts lessons. So let's start. We will need a copper wire, some electrical tape, one AA battery, one nail, scissors, and some pins for testing. First of all, let's rub the copper wire around the nail. Like that. Make the coil as tight as possible. Now cut off the excess. Now strip the isolation. Then connect the contacts. Cut a piece of tape. And as it goes, one to the minus, and one to the plus. And so we get such an electrical magnet. Let's test it out. Well, thank you so much for watching. Don't forget to subscribe, leave comments and press like. Thank you one more time. Bye.
Working of electric bell. Let us study how an electric bell works to produce sound. In an electric bell, the terminals T1 and T2 are connected to a battery through a push-button switch. When the push-button switch is pressed, electric current flows from the dry cell to the electromagnet and then to the contact screw and finally to terminal T2 and again to the dry cell. Thus, the electric circuit is completed. When the electric current flows through the bell, the following effects take place. Electromagnet gets activated and pulls the soft iron armature strongly towards itself. The spring connecting the armature and the stud S gets under tension. The hammer strikes against the gong, which produces sound. The electric current flowing in the circuit breaks at the contact points, but the armature and hammer continue moving towards the electromagnet due to inertia of motion. As the electric circuit breaks, the electromagnet gets demagnetized. Thus, it cannot hold the armature. At this moment, the spring, which is under tension, brings the armature to its original position. As the armature returns to the original position, the electrical contact is re-established and electric current flows through the circuit. Thus, the armature is again attracted towards the electromagnet. In this way, a rapid make and break of electric contact takes place and the hammer hits against the gong, producing a ringing sound.
In around 1820, a Dutch physicist named Hans Christian Ørsted made an accidental discovery which opened up a whole new branch of physics that explored the connection between electricity and magnetism. In this video, we'll explore what this discovery was and what were its implications. So as the story goes, Ørsted was doing a demonstration in his lecture in which he had a copper wire through which he would pass some electric current. And on his table, there happened to be a tiny magnetic compass there. Now what he found is when he ran an electric current through that wire to perform some experiment, that magnetic compass deflected. That's it. This was the experiment that led to a great discovery. Now before we talk about what it was, let's go ahead and repeat that experiment. And so to perform this experiment, all we need is a wire, a battery to pass electric current through it, and the magnetic needle. Once we connect this, once we close the circuit, a current will pass through it. And just take a look at what happens to this magnetic needle. All right, here we go. Notice the magnetic needle deflected. That's it. That was the experiment. Now you may be thinking, what's the big deal about this experiment? So what? Well, think about it. So far, we could use electricity to create heat or light. But now for the very first time in the history of mankind, we have discovered that electricity or electric current can make things turn. Can you imagine what could be the applications of that? This principle is used in fans. It's used in your washing machines, in your electric drilling machines, and so on. It's the same principle on which our ammeter and voltmeters work, inside which you pass a current and there's a needle that deflects and shows us the reading. But more importantly, this experiment led us to a huge discovery. What discovery, you ask? Well, let's think about this. What can push on a magnetic compass? Magnetic fields. We've seen before that magnets can create magnetic fields, and when you bring a tiny compass in the vicinity of it, the magnetic field pushes on that compass. But over here, there aren't any magnets nearby. So who is creating a magnetic field that is deflecting this compass? Well, because the electric current was responsible for this deflection, maybe electric current produces a magnetic field around it. And this was a huge discovery. Why was it huge? Well, because earlier we thought that electricity and magnetism were two completely separate phenomena. But now with this single experiment, we are seeing that electric current is producing magnetic field, which means this gives us a clue that there might be some connection between electricity and magnetism. And that's why this opened up a whole new branch of science or branch of physics, which we called electromagnetism, in which we explore this connection between this electricity and magnetism. So Ørsted and probably some other physicists were pretty excited about this discovery. They wanted to learn more about the connection between this electric current and its magnetic field. So they started doing more experiments with this. One thing they immediately realized is that if you increase the strength of the current, then the deflection in the needle also increased. The compass deflected more. This meant that the magnetic field got stronger. So in other words, they found out that if you put more current, you automatically get more magnetic field. It kind of makes sense to me because it's the current that's producing the magnetic field. So I would expect that if the current increases, its effect would be more, and as a result, the field would also increase. Another thing that they found is if they keep the current the same, but they keep this needle at different places, at different distances from the wire, they found that the deflection was maximum close to the wire. And as they moved away from the wire, the deflection became weaker and weaker, smaller and smaller. This meant that the magnetic field is very strong close to the wire, but it weakens as we go farther away from the wire. That's another result. The field weakens with distance from the wire. And again, that kind of makes sense to me. This is very similar to what happens close to a magnet. If you are very close to a magnet, its field is very strong, its force is very strong, and as you go far away from it, the field weakens. And finally, they also wanted to learn, what does the field look like? What does the magnetic field lines look like? And we have seen before, to draw magnetic field lines, all we have to do is sprinkle some iron filings and see how they arrange, or keep this magnetic compass at different places and look at how it orients. So to do that, they made this wire vertical and made it pass through some kind of a rectangular piece of cardboard on which you can sprinkle iron filings or you can put all your magnetic needles. And when they placed the needles, they found out that the magnetic needles arrange themselves in this fashion. The red represents the north pole of the magnet and the blue is the south pole. Now remember, we define the direction of the magnetic field as a direction in which the north pole points. So over here the magnetic field is this way, this means over here the magnetic field is this way, and so on. And so if we replace these needles with arrow marks that represent the direction of the magnetic field, it would look somewhat like this. Can you see that these arrow marks are running in a circle? And so if we draw a continuous line connecting these arrow marks, we will end up drawing a circle. A circle centered at the wire. And this means that if you want to find the direction of the magnetic field at any point around the wire, you just draw a tangent to this circle. So we draw a tangent to the circle here, you get the magnetic field direction here. You draw a tangent to the circle there, you get the magnetic field direction over there. And of course, we'll get more practice to this, finding the direction of the magnetic field in another video. But this is true at all distances. Even if I were to keep magnetic needles close by, they would run in circles. Even farther away, they would all run in circles. And so the magnetic field everywhere around a straight wire carrying current would be in concentric circles. So that's another result that we find. The field lines are in concentric circles. They all have a center at the wire. And finally, we also saw that the direction of this magnetic field lines depends on the direction of the current. If we were to reverse the direction of the current, the field lines would still be concentric, but they will reverse their directions as well. Like this. And also notice how we have drawn these field lines. The circles are drawn close to each other, near to the wire. This is to indicate that the field is very strong close to the wire. You may remember that one of the properties of the field lines are if the field is stronger, then we draw the field lines closer to each other. And as we go away from the wire, the field weakens, and as a result, we draw the circles farther away from each other. So, what did we learn in this video? We learned that when you pass an electric current through any wire, it produces a magnetic field around it. This connected electricity and magnetism. And with further experiments, we explored the properties of these magnetic fields. And one important property we found is that the magnetic field lines due to a straight wire carrying current is going to be in concentric circles.